So, yeah, in theory, you would have learned a lot of this stuff in pre-calc, but nobody teaches it in pre-calc, so you probably didn't. Unless you had me as a high school, maybe. But John Jay and Cross. So, parametric equation. The root of that term is parameter. So that's the part that we need to really kind of delve into or dive into, whatever the right word is. So, but before we got to kind of lay the groundwork for it. Is this oriented the way I want it? Maybe. All right, we'll see. Plane curves, paths of motion. Right. So a plane curve is kind of a weird thing to think about, because once you realize that it's what you've been working with all your mathematical lives, you're like, all right, so why are we changing the name? Like, why are we calling it plane curves now? Why is it not just a curve? You know, slope of the line tangent to the curve. You know, graph the curve on a given set of coordinate axes. You know, like, it's just a curve. But now all of a sudden it's a plane curve. The issue is, when we get into 3 dimensions, we could have a curve, a linear curve, or linear dimensional curve, so something that exists in 2 dimensions, x and y, that can occur on various different planes, right? So you could have something that is on the plane z equals 0, which is your ordinary xy axis. X, comma y, comma 0, which would have no height, right? So it's your ordinary x, comma y, your Cartesian plane. But then if you throw in a z value of 1, a height of 1, now you have a new curve that's on its own plane, but not on that standard Cartesian plane that you know and love from algebra and pre-calc. Right? So it's a new curve on a different plane. So it's a curve with its own plane, therefore plane curve. All right? But they follow, or they demonstrate paths of motion. So in a manner of speaking, at least in this unit they will. Because a parametric equation, or a set of equations, take your ordinary x and y values and introduce a new parameter, t, generally t. So we parameterize your y equals x squared, y equals x, whatever, y equals a sine of x. We parameterize it so that it has a time component. All right? So, because if you think about it, like, you could follow a sinusoidal path. You know, maybe you're, riding a bike up and down hills, right? But there would be some kind of speed component in there. So I can follow the same path as the person next to me, but if it's a race, it matters who finishes the path first. So that time component ends up being an important characteristic that needs to be taken into account. So how do we do that? If we just have y equals a sine of x, you can't just say, okay, and it's really fast, or it's really slow. What you have to do is you have to develop new equations that relate the horizontal distance to time and the vertical distance to time. Right? That's where our parametric equations are coming from. Right? I honestly don't remember what I was going for with these blanks, but we'll see. We can use those equations to describe blank. An object has been, okay, sorry, I guess that's where. Oh. It's a smart board, so I have to be over here. Where an object has been or is going, yet we cannot tell you when. In order to be able to tell when an object is at a certain location, we need a third variable called a parameter. Is that how Oh yeah, like that's why I like the other interface and iPads and stuff like that. My board work is just awful. What's that? I do it. Huh. We want to claim that type, right? That should be a continuation. like lowercase w, part of the previous sentence. So yeah, it's rough when your 8-year-old son tells you that you're using punctuation incorrectly. And I tell him he sucks at math, so it's all. But it's extra funny because he's incredibly good at math. So, like, I don't know if irony is the right word. Projectile motion. So the classic example of an object in motion when you think of a projectile. We think about parabolas. But obviously, motion is not just limited to parabolic movement. You know, just the idea of throwing something in the air that had it fall down a couple of seconds later. Yeah, it's great. We can learn a lot from that. But how does that apply to a car in motion? Can a car's motion be described in terms of a parabolic relationship? I don't see why not. Now, if movement, yeah, you could say it pretty easily enough. It goes up a hill, it comes back down a hill. All right, fine. Position, horizontal, vertical distance, the relationship's parabolic. That part's easy enough. But if you're looking at a parabolic relationship having to do with time, now you're looking at something where maybe you're starting off at a slow rate of change, then you're speeding up, then you're slowing down and speeding up. You know, you could have some sort of oscillating movement like that. It could be trigonometric, it could be parabolic. So why do we go back to this? We go back to this because it's familiar. That's why every course that you've taken started off at some point, or at least got into the idea of a parabola. And I swear, I mean, if we had to do another example where you throw an object in the air, a rock, a ball, I mean, I try to vary it from course to course to keep it interesting, but it's still object being thrown in the air, a couple seconds later it falls down. What's the highest point? How long did it take to get to the highest point? Things like that. You know, so we keep going back to it, not because it's an easy problem to do, but because it's a good place to get started so that we could learn about the trig functions, the transcendental functions, you know, your exponentials and logs and things like that. So the boring parabola problem is how we get started. Curvilinear motion, 2 variables for position, 1 for time. We'll get to that in a minute. So anything, and we're still looking at something that's occurring really in 2 dimensions. So we're looking at this, we have a horizontal and a vertical, but we don't have any depth, right? So we don't have that 3rd dimension going on, right? Later on in the course, we're going to incorporate a 3rd dimension and see how that comes into play, which is parametrics, right? For this particular motion problem, x, y are continuous functions, the t, and the resulting path of the plane curve. Continuous function, the definition is there. There's the classic definition, which I think is this one. You know, you can draw the whole curve without picking your pencil up off the paper. And then there's the Calc 1. You had to justify continuity by using limits. There's a place for that in this course. It's not going to be the overall emphasis in this course. Right? So, like, we will prove some things as we go, but more or less, at least in the early goings, it's more about learning how and why things work the way they do. Right? So, what we have here are 2 parametric equations and a terrible graph that doesn't really show anything. But the 2 parametric equations are this curve with a time component imposed. Right? So we have a horizontal component and a vertical component. So what I want to do now is show you very quickly on the calculator. I know some of us wouldn't have the calculator yet, so it's just a very brief look. I'll show you again how to do it next class, but I do want to expose you to it tonight. So anyway, in your calculator, in the mode menu, so you click, select mode, and you have this wonderful menu with a whole lot of stuff that you have never had cause to change. Probably the biggest challenge has been bouncing back and forth between radian and degree and making sure that you don't forget to turn it back into the right form before doing a problem and totally botching it. Normal, in terms of the rounding, that's fine. Float, that's good. So you can see here we have function, parametric, polar, and sequential. So on some of your calculators, it'll just say par instead of parametric, but that's the same function. Right? So if you select that, it'll put your calculator in parametric mode. So you scroll over to it and hit enter. There's some other things that I personally like to have in my calculator. So I like the thick setting because I have vision problems. So the thicker the better because it's easier for me to see. I also like simultaneous because what simultaneous will do is if you're graphing multiple functions at the same time, it'll start graphing them at the same time rather than waiting for one to finish before it starts the other. Right? Because I mean, I think we've all been in that situation where you put a function in and it was the wrong function, and you're like, oh, I gotta wait for all this to finish now before I can go back and change it. But you don't really have to do that. You can just hit on and interrupt whatever you're doing. But if you put it on simultaneous, if you're graphing 4 functions at the same time, for example, it's going to start graphing all 4 of them in one shot. So it's going to go through the process slow. Right? So that's my recommendation there. Everything else should be fine. We're not going to... Oh, well, actually, while we're here, turn your stat diagnostics on, because there's exactly one 10-minute period sometime in March where we're actually going to use the linear regression function on your calculator. And so this, you'll just have a leg up when that happens. All right, so make those changes, quit out of here. In your home screen, nothing's changed. But now if I hit that, that x key, theta, n key that always just gave us an x and we weren't sure why all these other characters were on the key, if I hit that key now, it'll bring up a t instead of an x.
What was the last part you turned on?
I turned on the diagnostics, stat diagnostics. You have to scroll down a little bit. You got it? Good. All right, so it brings up a t instead of an x. So that's wonderful. But then you'd say, well, how do I put it in as x equals and y equals? Because when I hit y equals, all it allows me to put it as y equals. Except now it's all changed. So, I mean, I remember the good old days, the 90s. Actually, they weren't that good. It was right before everything that was like cool technologically was going to happen. So, like, it was that purgatory period in history. Anyway, like this. It existed, I'm sure, but this calculator, even though TI-83, for example, is called an 83 because it was created in 1983. So it should have already been like an old form of technology, but none of my teachers knew how to use it. So this was not available to me. And the idea of researching it on my own was not much of a thing because when we got our calculators back then, they'd also give us like a handbook this thick. And we'd have to utilize something called a table of contents in order to find the appropriate the section of the book and then read it. That wasn't going to fly. So no Google then. In fact, I think it was called something else at that point in time. So this is, I had to graph all these by hand. Not terrible, but not fun. In retrospect, it might have killed enough time in class that we didn't actually get to the really, really hard stuff in the course. So maybe it was for the best. I don't know. But anyway, I can type in 24 rad 2 t. Just make sure that t is outside the rad by hitting the right arrow. Negative 16 t squared plus 24 root 2 times t. And then, because they've already kind of given us a sense of the constraints here, based on just the scale, I can establish my window. Now, when I hit the window key, you can see that it's a little bit different too, because I have a new variable that I'm working with, which means that I have to account for that in my parameters. So, it's not just x min, x max anymore, y min, y max, it's t min and t max. So it's not only how far out it's going, how far up and down it's going, it's also how long does it take to complete the journey. Now, I have sense that it's a little bit more than 2 seconds to, I guess it's seconds, 2 hours, 2 days, whatever, based on this piece of information here. So I can say, all right, maybe I'll go 3. And if it doesn't hit the ground, maybe I'll go a little bit higher. I could also try to solve for that piece of information. That kind of defeats the purpose. I don't want to do that. I want the calculator to do it. So I'll put, you know what? I'll just leave it. 6.28 for some reason. It's stored in as 2 pi. I'll just leave that. That's fine. T step is the increments that you're going by. At this point, I don't really care, but you really want to be careful about not going too large on your T step. I'll show you what that looks like in a sec. For x min and x max, 0 to 80, based on that scale, 0 to 80. And then 0 to 20 for the y min, y max. With the scales at 1, that's fine, just to get a sense of the view. But if you want, you change your x scale to go by 10s, because that's what they did here, whoever they are. And the y scale also by 10s. This way your tick marks will line up too. So that's pretty cool. Then hit graph. And so it created the graph, right? Now this graph here, I mean, you'll just have to take my word for it, because I really don't feel like putting it back into function mode just to graph this parabola. But if you were to graph this parabola, you would get this curve. We just got the same exact curve with a completely different set of equations. It's just a question of, well, how on earth did we come up with those equations? That's what the substitute is. Crikey. So the graph right there. Let's make that 0, and then we'll go by 10. Yeah, there you go. Yeah, your T-step was huge. So that's the next thing I was going to talk about. Like, if you go too big on your T-step, and I didn't need to go out to 6.28, so I'll make that 5, and I'll go by 2s. My T-step of 2, and hit graph. That's not a parabola at all. I mean, if you blur your vision, it maybe, I don't know. I mean, my vision's always blurred, so everything looks like a parabola to me. But yeah, that's not this. So the calculator has an overly linear way of thinking. So when you ask it to graph a function, what it does is it takes, not infinitely many because it's a finite base calculator, but it takes as many points as it can on the domain that's appropriate. So from 0 to 72 or whatever it is, I guess it's 0. But on that interval, it'll take an x value of 0, 0.1, 0.2, 0.3, 0.4, whatever, and then plot those points and connect them with little line segments. But it creates the points so close together that those line segments appear to form a curve, right? And that's what the calculator's been doing all along. But when I change the step, what I'm telling the calculator to do is give me a point every 2 seconds. All right, so it'll give me a point at 0, the beginning of my domain. Then it gives me a point at 2, which corresponds to this location. It plots a point. And then 2 seconds after that, it plots a point. And then connects it all with straight line segments. All right, so, I mean, you can come up with some funky shapes. Hey, if I made it a 0.75 instead of a 2 for my T-step. Every 3/4 of a second, it plots a point and ignores everything other than those points and connects them with straight line segments. But if I make it too small, all right, let's make my T-step like, all right, I'll play it safe, 0.001. What could possibly go wrong? I mean, you could be waiting a couple seconds. And if you go too small, I did that once just to be a wise guy. I made it point, like, oh, yeah, even the calculator says, no, relax, dude. Yeah, it's still. Yeah, you get too small, it's like, it's not happening. So let me do 4.
You just did 4.
No, he was.
So, I did something smaller than this, I forget what I did, but it was basically me hitting graph and then teaching for like the next 40 minutes, and it was only like a quarter of the way through the graph. And that emphasized the point enough where it's like, you're taking a test, you don't want to have to wait for this to finish graphing because you selected a course instead. Right? So, yeah, look at that. I probably get a whole problem. But yeah, we're still in definition mode here. I'm going to show you some calculations here, but in terms of the sketching part of it, it's really just coordinates. You just have to identify what the coordinates are. Just the last little fill in the blank here. The equation is given by x equals f of t and y equals g of t are parametric equations for c. The parameter is t. The trajectory of a plane is the direction that the curve is being drawn. So I keep walking over here as if there's a pen that I could write on the screen, and that would be wonderful, but there isn't. Now I'm self-conscious about my marker usage skills.
Is the delay on that pen must be too?
It pisses me off. I mean, it's the 21st century, you can't get something that
I can imagine writing that delay.
I just have to believe that it's going to come through the way I want it to. It's infuriating.
You ever send a package with your finger?
What's that?
You ever send a package with your finger?
A package.
Like one of those package forms you have.
Yes.
Oh, yeah.
You don't see it later, so you roll over like all your letters. It's gonna make sense.
Like you write like the world's best signature, and then there's like 3 dots on it, and the guy's like, yeah, that's fine. I'm like, oh, so basically anybody could have signed for this package. Wonderful. Orientation or direction. When sketching a plane curve, the direction of increasing to your orientation of the curve is indicated by little arrows indicating which direction the curve is moving. Oh, when the value of the parameter t increases. And that's an important thing because, I mean, I could ask you to graph a parabola, but who's to say that the parabola is showing an object going from left to right? Maybe the parabola has the object going from right to left. Okay. Same idea with like a circle. You know, once we get into polar functions, you'll see it gets a little funky. Like, who's to say we're going counterclockwise around the circle? We could be going clockwise, right? And it would matter because I call it the Medusa analogy. It's like if Medusa's standing over there, and you need to make a half turn, so you need to do an about face. She's standing over there. If you look at her, you're turning the stone. So it does matter which way you turn, because if I turn left, I'm going to turn the stone, but if I turn right, I'll be safe. Right? So direction is important for obviously more complicated engineering and mathematical relationships, not just fictitious scenarios. But yeah, it is important, and we denote the direction of the movement just by indicating it with little arrows along the curve. And I'll show you what that looks like in a second. The good news is some of this stuff is really easy, or at least now is easy because we have graphing calculators, and those graphing calculators should be used to their fullest potential short of cheating. Right? So when I have x equals t squared minus 4 and y equals 2t, I can easily figure that stuff out. I can plug in those t values by hand and do all that work. Or I can go to y equals. Oh, it's still thinking. All right, I want it to stop. I want it to stop thinking, so I'm just going to hit on. On interrupts anything. All right, so now it's done, whether I want it to be or not. I get rid of this stuff. T squared minus 4 and 2t.
We'll change the stuff.
Yeah, we're going to change the step. So I want this to go from -2 to 3 by 1s. So window, -2 to 3, going by ones. Honestly, I don't really care about the x min and x max and all that stuff, because I'm going to go to the table, get some coordinates, and in worst case scenario, I'll go back and adjust those later. All right, but this is what I want in terms of my good window, for at least as far as the t's are concerned. So second graph to get to the table. Some schmo changed the settings on it. All right, so if you have an incomplete table, go into table set, second window, and make sure it's on auto. There is really, I mean, I've been doing this long enough. This is year 19 teaching. It's a long time. It's long enough that like technologies have changed throughout my career significantly. Like I started off with chalk. Like there were no iPads. So like there's been an evolution. In that period of time, I have not come up with any reason why this should be set on anything other than auto. Right? The people who say that you should set it on X, that's a better way to have it set up, they're only saying that because they don't know how to use the features that are pre-installed in the calculator appropriately. Right? That is really the only reason why they're doing that. So, in this course, you'll learn the appropriate features and you'll never have to change it to X. So, now I'll go into my table. You can see how fired up I get about that. Now I have a good window, or a good table set, along with the corresponding values. I can, bless you, I can do that. Oh, I have this because I want to pin it to the taskbar. I can get lazy from time to time, and this is one of those moments. And again, yeah, I mean, you've seen my handwriting, so anytime we can avoid me actually writing is probably a good thing. All right, but these are the values that will go in the table. All right, those are supposed to be zeros. Once we get situated in a new classroom that doesn't have a smart board but has the projector, like the way I like it, you'll be able to read my handwriting. The smart technology is not what it's cracked up to be. In fact, this is a good 20 years old. Anyway, so we want to plot these points, right? So this is the thing, though. We're going to plot x against y, because how do you visualize what t would be in terms of a new axis? It doesn't really play out that way. Okay? So it's the x-axis against the y-axis, but we still need to indicate along the way what's happening with t. So I'm just going to put some arrows on here real quick. I don't want page recording. Why would I want that? And what is this? Where did that come from? So I'll take this as a typo. I mean, again, this is one of those things where I'm saying, like, I'll take anything that'll improve my notes. I think that this graph could use some improvement. I mean, you can barely see the numbers, etc. So, I just wanted to accentuate those axes. So I'll take that. So it's x against y. Normally, I don't bother labeling the axes because I just don't care enough. But in this case, it's important because you do need to know that it's the x values against the y values that we're concerned with. All right, so 0, -4. I mean, you could barely see it, but not, I mean, it's going by ones anyway, so it's fine. Nothing's going to go off the grid, right? I don't think so. So 0, -4, -3, -2. Now it's out of whack. It's really aggravating me. -3, +2. 0, 4, and 5, 6. Is that here? Okay. 1, 2, 3, 4, okay, good. So we have this partial sideways parabola. So we're going to connect it from where time t is the lowest value and follow the path to where time t is the largest value. Right? So we're going in the increasing order of time. They said specifically for these coordinates or these values of t, so no arrows required on your curve, but or at least at the endpoints. But we do need to indicate the direction of this, because anybody looking at just the graph would be like, all right, cool. Are we starting here on the right-hand side and working our way downward in the counterclockwise direction, or are we going the other way? So we need to be clear that we're going in the clockwise direction so we can those points. So arrows. Just a few of them. I tend to go a little overboard. I kind of imagine it's sort of like a slope field where we're getting a direction of the flow. And I think it looks cooler this way. But, you know, you might choose to do it in other ways. As long as it's very clear what the direction, based on your graph, it's very clear what the direction of the flow is, you're fine. Some people put their arrows right on the curve, that's fine. I just think this looks like cool. And I like that. Later on in the course, we'll talk about, direction fields and things of that nature related to complicated functions and also three-dimensional situations. So we're going to expand upon this idea. So really, I mean, not too bad, right? Because you just plot the points. So this one is not only asking us to plot the points, but it's asking us to do something with it. All right. So what I like to do from time to time is just use the old creative pen and a nice little star and pop that on a question, because that's my way of saying I'd like you to do that one for homework. What I do is I'll do that repeatedly throughout the course so that we could start off the next class with some of the start problems from the previous class. Right? But it allows me to give you an opportunity to practice while also moving on. All right? So last thing we're going to talk about tonight is converting between rectangular and parametric equations. Very straightforward process. Actually, extremely straightforward. It would only require a little bit of perseverance. All right? That's the only thing that would be standing in your way, because conceptually, it is as easy as it gets. We just need to eliminate the parameters. Right? It is a process. Solve for t in one of the equations and plug it into the other one and simplify. Right? It can get a little tricky depending on the nature of the instructions. For those of you who had me before, you know this. I don't always ask you to simplify functions or put it in a particular form. But when I do, you need to do it. Right? So, like on a test, if I only ask you to simplify once, that's to be expected, but you need to go to a particular form. Right? So if you're unable to get it into the appropriate form, you lose credit. Okay? So, but I don't like to do that too often, because it doesn't always satisfy the requirements of the content, demonstration of knowledge, things like that. I think back to derivatives, or even limits. I mean, if you simplify enough, you get a nice clean answer, and that's wonderful. But if I just need you to demonstrate to me that you know how to take a derivative, all that extra algebra in the end is not advancing the cause. Okay? So, and that can be the same idea here. So once you get rid of the t, you have put it in rectangular form. Rectangular form is your ordinary x versus y axis type of situation. So Cartesian plane, the way it's always been, nothing new there. We want to get rid of the t. So all we're going to do is make a strategic substitution. I opened this and never took a second. Make a strategic substitution that allows us to eliminate the parameter t. Some cases it's very easy to see, and some cases it's not so easy to see. The default algorithm tells us solve for t, but maybe I don't want to do that, because maybe I noticed immediately that x is the same as 2t, and there's a 2t right now. So couldn't I just replace the 2t with an x?
Yeah.
It's direct substitution, so y would be equal to 4 minus x. Okay, so, of course it's the wrong way. That's what we want. So, nice easy way of getting rid of that parameter. It's not always going to be as simple. Look at this one. I need to isolate t. I mean, you have a choice of working with the t function, the x function or the y function. I think it's obvious that you'd want to work with the y one, at least initially, because all I have to do is multiply both sides by 2, and I get t equal to 2y. And then I could just do some direct substitution there. Right? I'm replacing that t with that. Okay, so I'm looking at x equals, oh, and that whole, like, requirement pre-calc algebra of, like, you have to have it solved for y in terms of x. Not always the case. Right? I'll take, all I'm asking for is rectangular form. So once I have this, we've accomplished the objective. Right? It's an explicitly defined function, which means it's solved for one variable in terms of the other. Cool. I have an independent and a dependent variable. Wonderful. This actually probably tells me more than what I would get. So if I solve this for y in terms of x, I would get some funky radical function. It's debatable whether or not you recognize what that would look like. But here I'm looking at this and be like, oh, this is the inverse of a parabola. All right, well, what's an inverse of a sideways parabola? Okay, so now I have a better sense of what's going on in this graph just by leaving it solved for y, solved for x in terms of y. You want to square both sides? Be my square this out. Be my guest. Simplify. You're welcome to do that. Not a requirement. If I needed to take the derivative of this, I might choose to simplify it a little bit more. And also, just a thought. Let's say the question asks you to find the derivative of y in terms of x, so dy dx. I can take the derivative of this as is. You know, actually, let me just do that real quick. So x, I'll clean it up, 4y squared minus 4. If I needed to take the derivative, so a little side example, find the derivative with respect to x of this whole bad boy, of x of y. I'll take that as a type. So what I would do is take the derivative of this. I wouldn't write dy dx. I'd write dx dy because it's the reverse. So it's dx dy would be equal to what? Dy. All right, but ultimately I want dy dx. So I need the reciprocal, right? I need the reciprocal of this. If I'm taking the reciprocal of one side in a proportional relationship, I have to take the reciprocal of the other side. So 1 over dy. So, I mean, what purpose would it have served to solve this for y in terms of x? I mean, I'd have a function that solved for y in terms of x. That's the only purpose. Because after that, I could take the derivative, but then it would involve chain rule. It wouldn't be pretty. I'd have a plus or minus in there, and it's not fun. But this, much easier to work with. Okay, so just kind of roll with it. Don't shoehorn your solution into a particular form. All right. Don't make it so it's like, well, it has to be y. So you got to leave that box. All right, forever. It was never important. It was, you know, this is what it was important for. It was important to develop some consistency in Calc 1 and Calc 2. Right, because whoever, you know, Rene Descartes, when he invented the x and y coordinate axes, he could have very easily made y go along the x-axis and x go along the y-axis. So it's all arbitrary. The last one, the most important one, the one that talks a little bit about trig, I need to get rid of the theta. That is the last thing we're going to do tonight, so you're off. This is the trickiest kind of situation because there's a bunch of different avenues that you can use to come up with a solution here, and they're all right. It's just a question of what you prefer, what kind of speaks to you when you see a problem. You know, if you happen to know Pythagorean relationships, then you're ready to rock and roll. So the most basic Pythagorean relationship is that cosine squared theta plus sine squared theta is equal to what? 1. Alright, so this is the rule. This is the truth. Alright? I could actually put a little, triple equal sign to say that it's equal by definition. It's equal mathematically, it's equal by definition. Like, the world would stop spinning if this was not true. Right? That's how important it is. Right? The good news is, I know based on these parametric equations, which does not relate x and y with time, it relates x and y with some unknown angle theta. So that's a different departure, and it's a different way of thinking. We can parameterize a function any way we want. It's not always going to be related to time. You can just create a new variable and parameterize in terms of that new variable, in this case theta. So if I know that x is the same as cosine, then I'd be saying that it's really x squared. Y is the same as sine, so it's really the same as saying y squared. And now I have a rectangular equation. Identifying, having a sense of what that rectangular equation is very important, because you look at this and say, all right, cool, I got an equation that's got x's and y's in it. I don't know what the hell it is, so like, what does that do for me? But if you happen to know that this is a circle, specifically the unit circle, now you're moving somewhere. And in fact, this is the parameterized form, or the parametric equations for unit circle, 0 to 2 pi. All right, so I'm already hitting you with the unit circle. That's how important it is. All right.
Doesn't it just come out to the equation itself?
When you solve for your domain,
And then incorporate
You have another perfect.
so
See that?
see that?
So that.
it. And try to like add some solving incorporate on
No, are you talking about using inverses?
the. No, I sort of.